Hi everyone. In this video I want to talk a little bit about the Quantitative Analysis Lab Experiment 6. Now at this point you have already done absorbance, and in this case we're going to use blue food coloring, and we're going to determine how much blue food coloring is in a sports drink like Gatorade, or how much blue food and I should say how much food coloring is in blue hard candy, like a Jolly Rancher or something like that. So this is basically what we're going to do. Now, in experiment 2, we went over the theory of absorbance, why molecules absorb light and things like that. You might want to review that, okay, if you don't remember about that, because it'll help you write your pre-lab. Included in there is things like Beer's Law, and also included in the experiment 2 video are things like practically how to blank the spectrophotometer. So that is basically what we're looking at. Now, when it comes to blue dye, I'm going to talk first of all about red dye mostly, and most of this video is going to focus on the data analysis on a piece of paper. I strongly recommend you translate that data analysis to Excel, but I do want to talk about it on a piece of paper. But before we do that, I want to talk briefly about how to make this calibration curve. Now, if you took General Chemistry 1 here, you did this several times, so I don't want to spend a lot of time on it, but I do want to briefly talk about it. So what you're going to do is you're going to take solid blue food coloring, okay? If you thought those little bottles of food coloring that you know, maybe you used when you were a kid from the grocery store were messy, the solid takes it to a whole nother level. So please, please be careful with the solid blue food coloring, and please don't get it everywhere, okay? Because it gets on everything and it stains everything and it's bad. So please just be careful with it. That being said, you're going to use some blue food coloring. You're going to take about 100 milligrams of the blue food coloring, and you're going to put it in a 250 milliliter volumetric flask. And in fact, you're going to measure the exact amount of blue food coloring that you take. So make sure you write that down. So you don't need to do exactly 100 milligrams. If you take 96.23 or 96.2 milligrams, that is totally fine. All right. So just take what you need. Then you're going to dilute that such that you make a 5-point calibration curve with absorbances between about 1 and about 0.1. You'll see here in my calibration curve, I didn't get quite as low as 0.1, but I got up around 1 for my higher value. So this is what you're going to do. Now there are several ways you could do this. You can use Beer's Law and look up the molar absorptivity coefficient and calculate the concentration that should give you an absorbance of around 1. And that may work. If you want to do it that way, that's totally a reasonable way to do it. You can also do it kind of empirically by taking your 90 whatever milligrams of blue dye, putting it into 250 milliliter volumetric flask, and measuring the absorbance. If the absorbance is very high, around 2, dilute it by 10 times. Measure the absorbance again. If it's still around 2, dilute it by about 10 times. Measure the absorbance again until you get something that's closer to 1. And then you could basically go from there. Because your absorbance ranges are between 0.1 and 1, you can dilute by 10 times and be safe that you'll fall on the calibration curve. But if you have an absorbance around 2 in the instrument, that essentially means that you're just blocking the light, and it may not be, it's very unlikely to be actually, in the linear range. So meaning if you have an absorbance of 2 and you dilute it 10 times, it's not going to become an absorbance of 0.2. But if you have an absorbance of 1 and you dilute it 10 times, it's going to become around 0.1. Then what you want to do is kind of experimentally, and I'm not giving you exact details here, I'm just kind of giving you a strategy of how to do this, is you want to find something with an absorbance of around 1 by diluting by 10 times until you get an absorbance that is on the linear range, and then doing a calculation to figure out what would give you an absorbance of around 1. Make that around 1 solution. Then 80% of the 1 solution and 20% water, 60%, 40%, 20%, something like that, in order to do that. And you could just take, 2 mils in 10 or 5 mils in 25, 4 mils in 10 for 40%, or 10 mils in 25, whatever you want to do to make these solutions on your calibration curve. So your goal here is to make a calibration curve, okay, with 5 points ranging approximately from 1 to 0.1. We're not super picky if you're a little bit lower than 0.1 or a little bit higher than 1, but 1.2 is too high, okay, and 0.08 or lower is too low, but approximately 1 to 0.1. the r squared of your calibration curve should be 0.99 or better. Remember that the r squared tells us how well the data fits the curve. So here you can see the linear fit goes through all the points, and I have 0.9993. If you have a bad point, just remake it. Again, this is 100% of whatever you find, 80%, 60%, 40%, 20%. That's a reasonable way to do it. So I know I haven't given you all the details on how to do that, but I hope I've given you a little bit of a strategy to think about as you try to define your own strategy for how you want to do that. Now, what you're going to do is, once you have your calibration curve, my calibration curve is here. Notice that I'm using red dye and you're using blue dye. So these molarities probably will not apply to you because the molar absorptivity coefficient of red dye and blue dye are different. However, that being said, I have the calibration curve of red dye number 40, and in other videos we have looked at, different examples of the same thing. So these numbers may not apply to you. Now in my case, I'm going to measure the absorbance of a red sports drink and a red candy. You're going to do a blue sports drink and a blue candy. So in this case, 1 milliliter of the red sports drink was diluted to a total volume of 25 milliliters. So essentially I took 1 milliliter of sports drink, put it in a 25 milliliter volumetric flask, and filled to the line. And the absorbance of the resulting solution, as put in the spectrophotometer, was 0.638 AU. Note that I only need to do this calculation once. You're going to need to do this for 3 samples of sports drink. Said another way, use Excel. Use Excel to do this. I'm not going to show you how to do that today, but because I want you to have practice to do that. However, I am going to show you how to do it on a piece of paper. So the first thing that I want to do is I want to calculate the concentration of the red dye in the sample. All right, because I diluted this sample. And then I want to find the concentration of the red dye in the sports drink. Notice these are not the same thing because I didn't measure the red dye in the sports drink directly. Why not? Because if 1 in 25 is 0.638 AUs, then the full red sports drink is certainly not going to be on the calibration curve. It's certainly not going to have an absorbance between 0.1 and 1. Because I diluted it 25 times, and here it is. So it'd be theoretically 25 times higher than that. So this is basically what I want to do. So I want to first find the concentration of the red dye in the sample. Well, what am I going to use to do that? Y equals mx plus b. Y equals 23,000 x minus 0.012. Now, what is this? Well, this absorbance is a y value. So I'm going to put in 0.638 as my y equals 23,000 x minus 0.012. I want to add 0.012, add 0.012, and I'm just going to move the x to the other side. 23,000 x equals 0.638 plus 0.012 is 0.650. Divide by 23,000, divide by 23,000, and I find that x equals 2.83 times 10 to the minus 5 molar. So this is the concentration of red food dye in the sample, the 1 to 25 dilution of the sports drink. Okay, notice that I got this using the calibration curve. Also notice that you don't want to have to do this math a bunch of times. Do this in Excel. This you can be easily done in Excel once you get the calibration curve. And then you can just drag it over and do it in the other cells, as we've shown you several times. Now I want to find the concentration of red dye in the sports drink. So in order to do this, I'm essentially going to use C1V1 equals C2V2. But I'm going to use it as a slightly modified version. I'm going to call it the sample, that's the 1 to 25 dilution, and the sports drink. So C sample times V sample equals C sports drink times V sports drink, because I diluted the sports drink. So I can use the dilution equation. It's the same as C1V1 equals C2V2. I just changed the titles here. Okay, now the concentration in the sample, that's what we just found a second ago using the calibration curve. 2.83 0.83 times 10 to the minus 5 molar. The volume of the sample was 25 milliliters. Of course, I didn't measure all 25 milliliters in the spectrophotometer because it won't fit in the vial. Only about 7 milliliters will fit in there. Okay, but it doesn't matter. That was the original solution that I used, so that was the total volume, 25 milliliters. Equals C sport strength, that's what I don't know, times the volume of the sport strength that I originally used, which was 1 milliliter. Now, because I'm going to use a pipette to do this, it's going to be 1.00 milliliters. Poor wording here. I should have put 1.00 milliliters. And I find that the concentration of the sport strength, when I do this math, is equal to 7.08 times 10 to the minus 4 molar. So, the concentration of the red dye in the sports drink is not the same as in the sample, which makes perfect sense because I diluted the sports drink. Why did I dilute the sports drink? So it would fall on the calibration curve. You're going to do this 3 times, and you're going to calculate the average and the standard deviation and the relative standard deviation, and you're going to talk about the precision of the measurements. Okay, so to briefly recap, we generate a calibration curve with concentrations between 0.1 and 1 and an R squared of around 1, 0.99 or better. All right, if you have it not 0.99 or better, try to figure out which point is bad and remake it. We get that calibration curve. We use that calibration curve to find the concentration of dye in a sample which is diluted from the sports drink, such that the absorbance is between, in my case, about 0.18 and about 0.92 on the calibration curve. Okay, so that's basically what we're doing. Then we find the concentration of the red dye in that sports drink, or in that sample. We use the dilution equation to then find the original concentration in the sports drink. You use Excel to do this math because it'll be easier because you have to do it 3 times. You calculate the average, the standard deviation, and the relative standard deviation, and you comment on the precision. That's basically what you're going to do. The last thing that I want to point out about this is these volumes are made up for red dye, okay, and some made up sports drink. You are not using the same sports drink or whatever. 1 in 25 may not work for you. You might have to do 1 in 10. You might have to do 1 in 50. You may have to do it twice, right? You might have to dilute it 1 in 25, and then it's still way off the calibration curve, and you have to dilute it 1 in 25 again. So you have to do this math twice. This is not exactly what you're going to do. It's not meant to be exactly what you're going to do. It's just meant to give you an idea of how this reaction is, or how this experiment is going. Next, let's look at the candy. Good news for the candy. Okay, we have the same calibration curve. This is just a copy of the exact same calibration curve because it's the same dye. Okay, in my case it's a red candy, in your case it's a blue candy, but either case it's the same dye. So we can use the same calibration curve. In my example, again, just like the previous one, it's a made up example. Don't expect your numbers to be exactly the same. Okay, I crushed up the candy and a 0.312 gram candy sample. So 0.312 grams of candy was dissolved to make 100 milliliters of solution in a volumetric flask. The absorbance of the resulting solution was 1.14 AU, so a little above 1. So the solution was diluted by half, 5 milliliters in a 10 milliliter volumetric flask. The absorbance of the diluted solution was 0.562 AU. So a lot going on here. Again, don't expect you're going to have to do exactly these things, okay? These are just the things that I'm doing to show you kind of what's going on, but they're not the exact things you're going to need to do. So the first thing that I want to do is I want to figure out the concentration of the red dye in the diluted sample. Okay, so this is the diluted sample. So what we're going to do is we're going to use y equals mx plus b, just like we did before, but this time my y value is 0.562 equals 23,000 x minus 0.012. All right, so we're just going to use the same exact equation. Again, Excel makes this helpful for you because you've already typed this into the computer. You just copy and paste it. Now it'll do it for your values here. This should be 562. Sorry, not 522. All right, when I do that and I solve for x, which I just showed you how to do a minute ago, I get 2.50 times 10 to the minus 5 molar. So the concentration of red food coloring in my diluted sample, after I crushed up some candy and put it into a 100 milliliter volumetric flask, I found the absorbance was too high, so I diluted it by half because it's close to the linear range. And you can see this is about half of that. And this is what I got as my concentration. Well, in this case, since I had to do that second dilution, I need to find the concentration of the red dye in the candy sample. I've called it here. So here, the C sample, or C diluted sample, times V sample equals C candy sample. Notice that it's not the actual candy itself, it's just the original candy sample times V candy sample. In this case, my concentration in the sample I just found, 2 times 10 to the minus 5 molar, times the volume of the sample. Well, the volume that I used of the original sample was 5 milliliters, but I diluted it to a total volume of 10 milliliters. So that was the volume of the whole sample. The concentration of the original candy sample is a thing I don't know. That's my x. Times the volume of the candy sample. Well, here I used 5 milliliters of the original candy sample, which again was diluted in 100 milliliters. We'll take care of that in a minute. When I do that, I find that the concentration in the candy sample was double the concentration in the original sample, which is 5 times 10 to the minus 5 molar. All right, because I diluted it by half, the original sample had double the concentration. So now I have the concentration in the original candy sample where I took the 0.312 grams of candy and dissolved it in 100 milliliters of solution. Now, it asks for the concentration of dye in the candy. The units here are kind of up to you. You could do grams of candy or moles of dye per gram of candy. You could probably do grams of dye per gram of candy. Gram of candy is probably a good thing to use because you're measuring the mass of the amount of candy that you're using. I guess if you wanted to figure out the mass of a whole candy, you could find the moles of dye per candy, and that would also be a unit of concentration. So you don't have to use what I'm using, but this is what I'm going to use. So the first thing is I have the molarity of the candy sample. So what this means is there's 5.00 times 10 to the minus 5 moles of, in my case, red dye per liter of solution. But in my case, I used 100 milliliters of solution, so times 0.1000 liters solution. The liters of solution will cancel out. Whoops, I didn't mean to cancel out that. I meant to cancel out that. And what you find out is that you have 5 times 10 to the minus 6 moles of dye. In my case, red dye. Okay, and this is the moles of red dye in 0.312 grams of candy. So if I take my 5 times 10 to the minus 6 moles of red dye, and I divide it by my 0.312 grams of candy, because that's how many grams of candy I originally started with, I find that there's 1.60 times 10 to the minus 5 moles of red dye per gram of candy. And this is a unit of concentration because I use the grams of candy instead of milliliters of candy. It doesn't make sense. The candy is a solid to use a volume. So this is basically what I did. If you want to do grams of red dye, or blue dye in your case, per gram of candy, that would be perfectly reasonable as well. And all I would do is simply multiply by the molar mass of the dye in order to find that. So I hope you found these two examples helpful for finding the concentration of, in my case, red dye in candy. and for finding it in the original sports drink, because these dilutions and things are going to be required, but again, not in the exact same way that I am showing. Another practical note is when you crush up the candy, you're going to want to use it relatively quickly. It depends on how humid it is outside, but the sugar tends to interact strongly with water molecules, and then you end up with like sticky stuff, and that's not ideal. So when you crush it up, it won't stay that nice powdery stuff for very long, again, depending on the humidity. So basically, you're going to want to use it relatively quickly. So I hope that you found this video useful. I know I didn't explain how to do everything. I didn't explain the Excel part. I didn't really in detail explain how to make the calibration curve. So those are things you're going to want to think about before you come to lab, to make sure that you have a good plan for how you're going to make that calibration curve. And you also have a good plan for how you're going to make all of your calculations in Excel. And when I say a good plan for how to make all your calculations in Excel, the single best thing you could do is have your Excel file ready to go before you come to lab. You can use my example calculations here if you'd like, in order to test it out, because it gives you data that you could plug in there, and then you just plug in, of course, your own data as you do the lab. So thank you for watching the video, and I hopefully you found it useful.